Mr. Cox. I'm here to tell you about... What is that? That's the sun. That's right. It's the sun. How did the sun get to how it is today? We're going to talk about the sun. Okay? Okay. Pretty familiar picture, right? The sun as we know it exists today. But it didn't always exist. And it wasn't always like this. So we're going to talk about kind of the life cycle of a star. All stars start out as this nebular cloud of gas called a nebula. And we see these strewn all over our galaxy. Beautiful pictures of these different nebulas at different stages of their lives. And in these nebulas are the factories that produce these different massive or smaller stars. So, something like this image, right? This image is an image of a nebula out in space right now, and inside here is the workings of the beginning of a star. Our star started out as this, and this clump of dust and gas over billions and billions of years started to condense and got really small and really small and really small into what's called a protostar. Okay, so we started out as a nebula, we moved into a protostar. So if we're filling in these notes, right, all stars are going to start out as nebulas, all right? And we talked about the nebular theory when we talked in the space notes about what the hypothesis behind how we think our sun was formed, okay? Now, as that clump of gas and dust, mostly hydrogen and helium, condenses and gets much more dense and dense and dense, and more dust and gas, more condensed and condensed and condensed, it gets to a very dense core known as a protostar, okay? As that becomes more dense, the gravitational energy grows and therefore could draw more particles into it, making it larger, adding to its mass. Now, each time that it adds to its mass, the core gets much more dense. Well, what also happens is that the particles bang into each other and rub into each other. Well, what happens when objects rub into each other or bang into each other? That's right. Friction causes heat. And so the core of the protostar begins to heat up and heat up and heat up and heat up really, really, really hot until we get to somewhere around 10 million degrees, and all of a sudden something miraculous begins to occur. These hydrogen atoms, which are the smallest atoms that we know of, start to fuse together into bigger, heavier elements. Okay? So this increased gravitational attraction causes the star to begin to heat up because of the friction and the particles smashing into each other in the core. Eventually the temperature gets above 10 million degrees, and that's kind of the light switch. Once the core reaches 10 million degrees, it's like a light switch. Hydrogen atoms begin to fuse into heavier elements called helium. And when that happens, a process called nuclear fusion begins to occur. And a very small part of the hydrogen atoms is converted into a massively large amount of energy. And that energy is light energy, heat energy, amongst other types of energy, ultraviolet radiation energy, all of those different types of energy. That's all converted from a very small amount of hydrogen atom mass. Okay? A star is born. So, if we look at this, there is a life cycle for a star like our sun. Okay? A star like our sun. Here's a stellar nebula. And as those gases and dust start to condense and condense and get hotter and hotter and denser and bigger, more gravity, we get nuclear fusion begins at 10 million degrees. So we have our star today. Our sun is in its average star life. Okay, so if we think of this like a life cycle, here's the infant, here's kind of the teenage years, and as we get past the teenage years, we get into some other areas as we get older in our star life. So right now, we're right here, right? We're loving the sun, the energy that it's producing. There's plenty of hydrogen in the core that's converting into helium. But if we're pulling hydrogen and fusing it into helium, eventually what's going to happen? What are we going to run out of? That's right, we're going to run out of hydrogen. And the moment that that happens, we start to convert from an average star into a red giant.
Amira Fox, please report to the main office. Amira Fox, please report to the main office.
I don't know what that is. Right? So now we've got this nuclear fusion. So when small nuclei are combined, fused to form a larger nuclei, that's what nuclear fusion is. Right? We're fusing two atoms together. This converts a small amount of mass into a lot of energy. And there's kind of a three-step process. In the end, 4 hydrogen atoms fuse together to make one helium nuclei. Okay? So 4 hydrogens, bam, 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 and the nuclei of those hydrogen atoms fuse together. We're not talking about like, 2 balloons, right? And we just tape the balloons together and we can untape them and no, it would be like 2 balls of clay that you mash together. Once you put those balls of clay together, you cannot get them apart. Okay, so they fuse together, and when they do that, a little bit of the mass of the hydrogen atoms is converted into a massive amount of energy. Okay? Majority of the sun's mass exists as hydrogen and some helium. Majority of it. But eventually, we will run out of hydrogen. And most of the sun will be helium. Okay, so let's continue. As the sun runs out of hydrogen to fuse, its temperature rises and it will begin fusing helium into heavier elements like carbon, nitrogen, and oxygen. Because it takes more energy, because helium is heavier, so when we are smashing helium atoms together, that takes more energy. That's why the temperature rises in the sun. Okay? So, here is kind of an image of this nuclear fusion, right? Here's a hydrogen atom. Here's another hydrogen atom. Those two fuse together to make an incomplete helium atom, right? And then we have the same thing happen again. Hydrogen and hydrogen makes another helium atom. Those two smash together, we get even more energy, and it's this chain reaction. So once we meet, what's the temp? Nuclear fusion? Once we meet that, we take hydrogen atoms, smash them together, and they fuse into helium, and then there's a massive amount of energy that's released. Now, once we start to run out of hydrogen, now the sun still wants to produce energy. So now it's going to take the helium atoms, 2 heliums, and smash together. The nuclei of those helium atoms smash together to make heavier elements like carbon, oxygen, and nitrogen. And it smashes those helium atoms together. And we're kind of in this transition period. Once the average star runs out of hydrogen, we start to heat up the core, and by heating the core up, it starts to expand or blow up like a balloon, and so the star begins to grow in size. Okay? As nuclear fusion begins to slow down, meaning we're running out of hydrogen, we're running out of helium, the star begins to cool and expand in size. So it's growing in size. Okay? Stars like the sun will eventually become red giants, and eventually and then from red giants they will move into planetary nebulas and finally white dwarfs. So if we go back to red giants, right? So if this represents our solar system, here is our sun, so to speak. So, as soon as we run out of hydrogen and we have to start fusing helium in to make nuclear energy, we begin to cool and we begin to grow and grow and grow. So, what happens is, right, we started out as a small sun, but we get bigger and bigger. Oh, we just engulfed Mercury. Now we just engulfed Venus. And here we go. We are now engulfing Earth and Mars and Jupiter. And we grow and grow and grow. Now, what you can see is, right, we still have the core of the sun way back here. And the core is extremely dense material. The bigger the star, the more dense the core becomes because it has higher energy to fuse heavier and heavier elements. Okay? So we get bigger and bigger and bigger. And what starts to happen is the sun loses its ability to hold on to its outer atmosphere because the atmosphere is so large that it begins to dissipate. It begins to move away because the sun's core has lost its pull, its gravitational pull, because it's too far away from the core. So the outer atmosphere of the sun begins to just float out into space. Okay? And it becomes a planetary nebula. And then once all of that gas and dust dissipates, what's left is the core of the sun, right? So as this planetary nebula continues to grow, right, the atmosphere starts to dissipate, and once all of the gas and dust has dissipated, what's left is a white dwarf. The extraordinarily dense core of the sun, and it's not going through nuclear fusion, but it is still emitting some light. It's just giving off. The rest of the heat that is in the core is being given off, and it will take millions and millions of years to give off the rest of that heat. Eventually, that white dwarf will eventually turn into a black dwarf because all of the energy will have been released, and this will turn into just an icy rock in the space sky. Okay? So that's kind of the life cycle of our sun, a star like our sun, a very average sized star. Now, as I showed you in class, our sun is a relatively small star in comparison. So what about those stars that are massively huge, right? Much bigger than our sun. What kind of life cycle do they take? Because it is slightly different. Okay? So we talked about this. Right? We start as a stellar nebula. There's a lot of gas and dust, and that fuses together, starts at 10 million degrees Celsius. We start nuclear fusion, and we are here for a period of time, right? This is teenage years, and then we move into a red giant once we run out of hydrogen. Okay, we start fusing helium. That takes more energy, so it raises the temperature, and it also expands the atmosphere of the star, making it bigger and bigger and bigger. Eventually, the sun loses its capabilities to hold on to its outer atmosphere, so it begins to dissipate into a cloud of lighted dust and gas, and eventually that dust and gas will dissipate, and we're left with a white dwarf. Okay? So what about stars that are bigger than our sun? Right? Stars that are larger than our sun will become red supergiants. Right? Ours became a red giant, but larger will become red supergiants. Now, red supergiants will eventually collapse with very high gravitational force and extreme temperatures and pressure, and it begins nuclear fusion again. So the star begins to grow, but then the core gets so gravitational hungry that it collapses on itself, and when it collapses on itself, it starts nuclear fusion again. Okay? Where our sun was not hot enough and heavy enough to start nuclear fusion again. This time, we have no hydrogen left. We've converted it into carbon. We've converted it into nitrogen and oxygen. Now we take carbon that's in the core and we make heavier elements like oxygen, magnesium, and silicon. Okay? Fusion continues until almost the entire core is converted into iron. That's the heaviest element that a core in a star can have. Once the core is iron, it stops nuclear fusion because it's the most dense that it can ever be. After the star has used up all of its energy, the core is completely iron. The core begins to collapse on itself because it's slowing down, it's cooling off, and it starts to collapse under its own gravitational pressure, and then will explode. That explosion, a supernova. Right? Leaving behind, after that massive explosion, leaving behind a neutron star. So that's supernova. Let's go back to this supernova. A supernova, in the matter of seconds, releases more energy than our sun will in its entire 10 billion year life cycle. In its entire lifetime, a supernova releases more energy in just a few seconds. Mind blow. All right. This is not part of your notes, so I'd like you to write it down. If the star is large enough, the supernova could create a black hole. So these massively large stars, instead of creating a neutron star, it may collapse after the supernova has exploded. It may collapse under its own gravity and collapse into becoming a black hole, where even light can't escape. Pretty crazy. Okay? So if we look at, right, we looked at what our sun, a star's like our sun, that's the road it will go. Now this is the road that a massive star will take, right? They both start out as stellar nebulas, right? And then intense gravity, intense heat until about 10 million degrees, massive star, nuclear fusion begins. Light is starting to be emitted, right? So we're turning hydrogen into helium. Once we run out of helium, then we turn helium, or I'm sorry, once we run out of hydrogen, then we turn helium into nitrogen and some oxygen, and then nuclear fusion begins to slow down. So the star begins to cool off and expand just like we did up here. But now this is a much larger star, okay? And eventually, the core becomes so gravitational hungry that it starts to collapse on itself again. Once it collapses on itself again, it heats up and starts nuclear fusion again. But this time, it doesn't have any hydrogen and helium. It's got carbon, and that carbon is turning into silica and oxygen and magnesium. Eventually, that magnesium and oxygen and silica will turn into iron, right? It will fuse into, make heavier and heavier elements, to make heavier and heavier elements into iron. Once that core becomes all iron, iron cannot fuse together anymore. It takes way too much energy to do that, and it's an extremely stable element, so it doesn't want to fuse anymore. So that core is kind of stuck. It's all ran out of energy. So now it starts to collapse on itself again. Collapse, 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 until enough gravitational collapse happens and we have a boom! Massive supernova explosion where in a matter of seconds, more energy is released than our sun has in its entire life. Pretty crazy. And then it can either, what's left is the core, an extremely dense core, or if it's so huge, that core could collapse on itself, creating a black hole where not even light can escape. Pretty crazy. All right. So that does it for the life cycle of a star. In class, we're going to watch a couple videos, and we're going to look at what our book says about this, but that kind of gives you the foundation of the cycle of a star. Please, if you need to, rewatch this, answer the questions, make sure that you can understand those notes. All right? Peace out, homies.